Send me an email about it. Yeah, then we'll talk about it. But sure. Yes, thank you. Yeah. That's your email. How week it is? It'd be 8. Or a pen.
Yeah. I can do that.
I don't matter. Tell whoever is in here. Turn off. We respond. Is that what is so probably
Good. That's that's just so interesting to me because like it's been I mean, it's pretty it's never just it's very right but it's like in between both fucking maybe it's expensive. Yeah, like $300 chat. Yeah, food brings. That's what I appreciate that. Everyone. It's just it's just without happy. I'd say how have you been studying for tonight? Yeah.
Really, it's just, because he's giving us the new card. All you need to know is, or like review is the whole thing. Chapter 4 in the textbook has an equivalent length problem. But it's pretty easy, it's just simple K equals F times L equal over D. Yeah. It seems like a lot of it's just to be able to understand the tables, how to read the tables, and find others and stuff.
I feel like you give us values, you know.
Yeah.
I mean, on schedule for the integrator to remember.
I'm sure he's gonna do that, cause I had a for econ. And give us like the full table, and we have to go to the table and find stuff for everything, so. Really, I'm mostly worried about the units.
You think like the last year's midterm I would give like conceptual ones too. Same person like his last year's midterm on
Oh, you did? Were there conceptual?
yeah, it was like 5 or 6 of them.
Yeah, I don't know. I mean, it's just fluid conceptual stuff.
And it's or the assumption means like what's an assumption not made, then we're using equation, and what you use a diagram or guy skills measurement one. What variables you use for if problems, what major loss, yeah.
It's easy. Yeah, that's,
Uh,
I just saw that online.
yeah.
It's on the idea.
Not on this thing.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, pretty good. Pretty good, pretty good. All right, so last time we met, we had the midterm exam, of course. So I just started grading them, and so literally just maybe about 30 minutes before I came here. So I'm nowhere near done. And so I don't think I'm going to try to get the grades done by Wednesday. But you know, I'm going to try my best to be there. But if not, you know, before the end of the week for sure. Okay. Okay. So I really have no idea in terms of, you know, how the grades are looking or anything like that. So, you know, probably have a better idea on this thing. Okay. So the plan for today, so we have about one more lecture or maybe about 3/4 of a lecture about static biomechanics. And so we have a couple more examples about the spine. I wanted to talk a little bit about common injury of the spine as well. And then after that, we're going to transition into the second half of the class, or second half of the semester, I should say, in terms of talking about human dynamics. Okay, because everything that we've talked about so far has been just purely static situation where the human body is just kind of still, no motion, no acceleration, no velocity. And so we'll talk about, you know, how do we actually go into that that realm of human dynamics. Okay. Okay, so that's the plan for today. You know, it would be the next homework 4. I think I'll have ready for you guys by Wednesday as well. So, you know, I at least wanted to give you guys the weekend off and off until Wednesday before we do anything new with this classes. So I'll have that ready by. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and jump in. So we'll come back to the slide in a second. A couple examples to do from the on the iPad. Okay, so let's go ahead and continue where we left off. So last time we met, last Monday, you know, we did a couple of examples in terms of, you know, the effects of, you know, lifting with proper technique, right? And so what we saw was that when you lift with improper technique, or you lift primarily with your back, it puts a lot of strain on your spine, which can lead to a lot of injuries. Okay. So today I want to kind of go on that same kind of vein. So very kind of similar, but talking more about kind of ergonomics and talking more about you know, more repetitive tasks. Okay. In particular, I wanted to talk about posture, right? And so posture is something that I don't know if maybe you guys are the same, but when I was growing up, my dad always like fixed my posture. It got to the point where it was kind of very annoying. But now I'm glad that he did, because you know it kind of helps with a lot of issues. Okay, so we're going to look at 3 different situations right now. So we're going to look at kind of different degrees of posture, going from really good posture to really poor posture. And seeing how that affects, you know, the muscle in your back, the joints on your back, things like that. Okay, so quite similar actually to the homework problem that we did, the very last one in homework 3. You know, but as an example instead. Okay. Okay. So here we have case 1. Okay, so case 1 will be kind of an example of kind of a good posture. Okay. And so kind of the situation that we're working with here is that, you know, let's say that you are or we're modeling someone that's at their job and they're working on something on a table in front of you, okay? And so in case 1, we kind of have the perfect, or we have kind of the best case scenario where, you know, whatever this person's working on is at an appropriate height for them and is close enough to them at the table so they don't have to bend down to work on whatever that is, okay? So case 1 is the good case. Good posture. Well designed. Okay. So let's look at another case. And so in this case, let's say that the workstation isn't quite as well designed for this person, right? right? So let's say that the person that we're designing for here is quite tall, right? And so what happens that if you give a tall person a short workstation, right? Then they're gonna have to bend down to do whatever they need to do, right? And so if you imagine, maybe this is like you're working at a restaurant, right? And so whatever ingredients that you're working with, whether you're chopping or anything, is too low for you. And so in order to actually work with it, you have to kind of bend down slightly like this. Okay. Okay, so this is case two. So case two here might be, workstation two. In case three will kind of be an exaggeration of this, where let's say that not only is the workstation too low, but maybe the object that he's working with is kind of far in the back of the table. Okay, and so in order to work with it, he has to bend down even further. All right, we have basically different degrees of poor posture, right? And so this is something that actually nowadays I think people are becoming a little bit more aware of, which is really good. But I think on a at least on a short-term basis, this is not something that really kind of crosses your mind all too much. Okay, but what you'll see is that over time, if you kind of subject your back to these kinds of conditions, it can lead to a lot of issues later in life. And so the important thing for all these, so we're gonna examine all three cases here. But in all three cases, we're not going to add any loads, right? So the only thing that's going to change in between these cases is the posture. Okay. All right, so let's see what this looks like, from a free body diagram point of view. And so the free body diagram is going to look something like this. So let's say that this line right here represents the person's back. Okay. And then the degree of bending or the posture for the person is going to be given by this angle here. Okay. And so the greater that angle is, the closer that angle is to 90 degrees, then we have better posture. Okay. But as we go from case one to case three, then that angle is going to get lower and okay. And so we have two weights here that are going to be counteracted by the muscle force, right? And so on the one hand, we have the weight of the upper body and the head. And so this is W1. The W1 here is going to be just the weight. Okay. And then we're going to have a second weight here, which we apply here. So W2 here is going to be the weight of the trunk, so the weight of kind of the lower back. Then opposing these muscle forces and making sure the back is still remaining standing is the muscle force. Okay. some of the muscle forces that we're mostly concerned about in the back are your spinal erector muscles, and so those are the muscles that kind of your lower back. Okay, so we'll call that FM. This angle here we'll call alpha. Okay. And then let's go ahead and label these various points. And so the point at the bottom here, this is of course going to be the joint. Okay, so we'll call this point A. So point A here is the lower back joint. Okay, so point A is the lower back joint. We'll say point B here is where W2 is acting. Point C is where the muscle force is acting. And then point D will be at the very end. Okay, so those points there are mostly just so that we can measure the distances. Okay. What tends to happen with these is that putting actual lengths on this on these figures tends to get pretty missed. Okay. And then we also need our joint reaction forces. So I'm going to define the joint reaction forces a little bit differently in this one, a little bit differently than what we're used to. Okay. And so instead of defining the joint reaction forces in the X and Y direction, I'm going to have one component of the joint reaction force going straight down the spine. And so we'll call this JA. And then we'll have another component of the joint reaction force go perpendicular to that. Call this J. So J sub A there stands for the axial component. So that's the joint reaction force that's kind of right in parallel with the spine. And then JS, the S there stands for shearing. And so that's going to be our shearing, the shearing component of our joint reaction force. Okay. Right. It's a small change. It doesn't make too big of a difference with the problem. Remember what we talked about before, that when you compute the joint reaction forces, you can kind of choose any set of perpendicular directions that you want, whichever kind of either makes the most sense to you or is kind of most convenient for the problem. So for this particular problem, just because for the spine, a lot of times we're interested in kind of what's the amount of compression that we're putting the spine under. Okay, and so we'll work with JA and JA. JA will be kind of exactly the amount of spine compression force that we're looking for. All right, and just as always, in these kinds of problems, what we're interested in is we're going to compute. We're going to compute the muscle force and the joint reaction forces. Oh, let me give you the lengths. We haven't done that yet. So all the lengths in this problem are defined relative to the back joint. Okay, so the distance along the spine, so we'll call it the distance between points A and B, is 0.15 h. Okay. For h here is a constant. H is just simply the height of the person. Okay. AC here is 0.2 h. And then all the way up to the head here, we'll say this is 0.3 h. Okay. And so when we solve this problem initially, of course, we're doing this, we have kind of the same situation all throughout, right? So the difference between case 1, case 2, and case 3 is simply just going to be the angle theta, right? And so all we're going to do here is we're going to solve this problem in terms of symbols as best as we can, and then we'll fill in kind of the numbers later, and that way we'll be able to compare kind of head to head in terms of how good the good posture is versus how bad the bad posture is. Okay. Okay. So let's sum the four. So let's go ahead and write our equations of motion. So we'll start with the moment equation. And so we're going to use the moment equation to solve for Fm. Okay, so let's go ahead and sum the moments. And so we've seen this many times before, so I'm just going to go fairly quickly here. Okay, so you have minus W2 times 0.15h cosine theta. Okay. And so the cosine theta there is just to get the horizontal distance, right? Because W2 is a vertical force. And so in order to get its moment arm, we need the horizontal distance between where the force is acting and the joint. Okay. And it's negative because it's a clockwise movement. Okay. Then we have the same thing for W1. So we have minus W1, 0.3 h cosine theta. Okay. Plus, and then we have the moment from the muscle force, Fm sine of alpha times the distance along the spine, which is 0.2 h. And that whole expression is equal to 0. All right. So we have everything here, and so we're going to assume that we know W1 and W2. So those are kind of easily obtainable. You can just weigh them on a person, it's no problem. And so if we solve for Fm, okay, solving for Fm here, we have cosine theta times the quantity 0.15 W2 plus 0.3 W1, all divided by 0.2 sine alpha. Okay. And so if you'll notice that we have a common factor of h in every single term in that expression, so we can factor that out. And since the right hand side of this equation is 0, we can divide both sides by h and get rid of that. Okay. So pretty straightforward. Kind of everything that we've pretty much everything that we've done up to this point. All right, and so once we have values for theta and W1, W2, and alpha, of course, we can just plug it into this expression to get numbers for F. Okay. So now let's go ahead and do the force balances, and so that'll give us expressions for the joint reaction forces. All right, and since our joint reaction forces are in the axial and shearing directions, I'm going to sum the forces in those directions. Let's go ahead and sum the forces in this direction. Okay. So from here we have JA minus W2 sine theta. Minus W1 sine theta plus Fm cosine alpha. So we add the trigonometric terms here to get the component of the force that's within that's in the direction of the spine or parallel to the spine. Okay. All this is equal to 0. And so if we solve for JA, because JA here is unknown, we have JA is equal to W1 plus W2 sine theta minus, or plus, excuse me. Oops. In the first equation here, the Fm term should be minus. So we should have plus Fm cosine alpha. All right, we can do the same thing in the shearing direction. So we sum the forces in the shearing direction. And what we get is Js plus W2 cosine theta plus W1 cosine theta minus Fm sine alpha. Okay, so 0. And once again, we can solve for Js. So Js here is minus W1 plus W2 cosine theta plus Fm sine alpha. So remember, this is a fairly typical task, and so we're not doing anything, not doing anything strenuous here. Right? So we're just working at a workstation. We're either standing up straight or bending. And so ideally, we shouldn't see too big of forces here. But sometimes it is enough to kind of cause some injury if you kind of repeat this over a long period of time. Okay, so let's go ahead and put some numbers in this. So let's first plug in some typical values for the W1, W2, and alpha. So typical value for W1 might be 0.18. W, where big W here is the weight of the person's body, right? So what we're saying is that the weight of the head, the shoulders, and the arms is about 18% of the person's weight. Right? A lot of your weight is centered around your core, and so where your trunk is, where your chest is, things like that. So W2, let's say 0.36 W. And I know I said last week that the attachment angle for your spinal erectors depends on your posture, but just for the sake of simplicity here, let's assume that our attachment angle is the same in all three cases. And so we'll assume that the alpha here is 13%. Okay. And so let's evaluate these together with different values for theta, right? And so let me go ahead and write down our three cases here. So case 1, case 2, case 3. And so case 1, this is our best posture. So let's say that theta here is equal to 85 degrees. For case 2. So it's not even that big a change, right? And so the difference between case 1 and case 2 is just 10 degrees. So we'll say that theta for case 2 is 75. And then for case 3, the worst posture, let's say that this is 60 degrees. Okay. And so case to case, when you first look at someone, it may not look like that big a difference, but biomechanically, you're going to see that it actually does make a really big difference. Okay. And so let me kind of present the results to you in a table. Right, so we have our three unknowns here: FM, JA, and JS. Okay. So we have three cases. So 85 degrees. 75 degrees. And 60 degrees. Okay. And so when we plug in the numbers here, we can get values for all of these terms here. Okay. And so in the best case scenario, our muscle force is about 0.209 W. Okay. So everything is going to be measured relative to the weight of the person's body. Okay. And so if you have good posture, your spinal erectors are only outputting a force that's about 21% of the weight. When you move that slightly off, right? And so even just a posture change of 10 degrees, so you're kind of bending over just very slightly, you're almost tripling the amount of muscle force that your spinal erectors have to exert. So that's a pretty big deal. And then if you tilt even more at 60 degrees, this puts you at 1.2 times W. Okay. And so a bad posture of 30% will basically force your spinal erectors to output a force that's 20% more than your own body, which is huge, right? And so let's look at the corresponding joint reaction forces. So for the axial force, in the best case scenario, your spinal column is going to be exposed to a compressive force of about 74% of your body weight. Okay. Once you kind of rotate out about 10 degrees, this increases to about 113% of your body weight. And then in the worst case, at 60 degrees, this is about 1.64 And then we have the shearing force. And so luckily, you know, since we aren't doing anything extraneous, you know, we aren't kind of, we aren't really trying to shear the spine. The shearing force is going to be mostly zero. But if you were to add any other external forces, so maybe this person's lifting something, or maybe there's a force that's being placed on their back, then the shearing force might not be zero. But since, you know, we're not doing really anything too exotic here, you know, we can assume all the shearing forces are zero. Okay. It's not that we assume, we computed it to be about. Right. And so you can see, you know, posture makes a really, really big difference. And so, you know, if you compare these forces compared to the forces that we saw in the examples last week, you know, these are of course going to be a lot smaller, right? And so when you're lifting a heavy object, of course, that's going to place a lot more stress onto your back than just, you know, just bending over and supporting your own weight. Okay. But the difference between, you know, having a really good posture, having your back almost be completely straight, versus a poor posture when you're kind of hunched over, you know, it makes a huge difference. And so just in terms of the muscle force, that's about a 6 times difference between 85 degrees and 60 degrees, case 1 and case 3. But even in the joint reaction forces, it almost doubles or more than doubles the amount of force that your back joint is being exposed to. Okay. And so this may not be something, you know, again, this may not be something that you feel immediately, right? You know, unless you know you're like me, whose back is kind of bad already at 32 years of age. I hope you don't become like me. You know, just bending over slightly, you know, for maybe about 10 minutes is not going to bother you too much. Okay, but imagine having to be exposed to that kind of every day just to kind of get your work done. Okay? So that's why, you know, there's been a big emphasis on ergonomics in the workplace and designing workstations that work for the human that's working. Okay. Because if you're going to be expecting people to work at these places for a long time, you know, you have to make sure that their bodies are going to hold up throughout that entire time as well. Okay. All right. Any questions on this? Okay. All right. And actually, you know, if you work at any place corporate nowadays, and Fullerton is no exception, you know, they actually give you training on ergonomics. Which, you know, you might think is like, oh, you know, that's good. They want their employees to you know, take care of their bodies. But in reality, you know, they just give you the training so you don't sue them later in life. And everyone kind of knows this case. Which is the case for the vast majority of trainings that we have. It's just for compliance reasons. It's not for they're not doing this out of the kindness of their heart for their employees. Okay. So I did have one more example with regards to the skull, but I think, you know, we're a little bit kind of behind already, and so I did want to move on to human dynamics today, and so we'll go ahead and leave it here, okay? And so let's talk about injuries of the spine, just so that we can start talking about human dynamics today. Okay. All right, so let me go ahead and skip ahead in this lecture slides here. Okay, so I have a few slides at the end here talking about common injuries of the back. Okay, so let's talk about lower back pain. So lower back pain is probably the most common pain that the vast majority of people experience at some part in their life. Okay, and so the stat there is about, you know, 85% of people experience it at some point in their life. You know, I would go on to say that probably 95, 99% experience lower back pain at some point in life. Okay. And so, you know, and kind of more on the financial side, you know, the lower back pain is probably the most frequent and expensive of all workers' comp claims in the United States. It's kind of a nice fun tidbit for that. Okay. And so, of course, you know, mechanical stress plays a significant role. Okay. And so if you have a job that's requiring you to kind of lift heavy loads on a regular basis, or maybe you are at a workstation that's not really designed well for you, you have to bend down a lot, then, you know, you're going to be a lot more susceptible to lower back pains. Okay. And kind of what's more common nowadays, that, you know, for a lot of jobs that require people to sit at their desk for long periods of time, if your posture is not good, if you don't have adequate back support in your chair, then you're much more likely to experience lower back pain. Okay. And the causes are very varied. So it can either be an acute injury. And so when someone says that an injury is acute, that occurred in kind of one big kind of instance. And so when you try to lift like a very heavy load and you tweak your back, so that would be kind of an acute injury, or it can be kind of like a stress type of injury, which occurs over many repetitions or a very long period of stress. Okay. And so, the vast majority of causes or causation of lower back pain is already kind of relatively known, but there are still some cases that are still kind of a mystery. And so because it's so common, there's still a lot of research going into it in terms of what's the best way to treat these people, what's the best way to kind of prevent these kinds of injuries. Okay. And you can see from the graph here, if you remembered, your spine is kind of broken up into several parts. You can see that injuries or pain in the lumbar spine, which is the part of your lower back, is by far the most common problem. Okay, fractures. And so fractures are another point of concern for spine biomechanics. Okay. And so these mostly occur from traumatic blows. And so if you're in a car accident or if you're struck in the head or something like that, that's usually how these occur. Okay. And so the most common type of fracture that occur in the spine occurs in the cervical section, so kind of near your head. And that usually occurs when you have a very strong blow to the top of your head, which kind of rapidly compresses your cervical spine, which can cause some fractures. Okay, and like we mentioned before, your spinal cord is housed within your vertebrae, and so any fractures to that area can compromise the protection of your spinal cord, and so your risk of things like catastrophic injuries like paralysis is definitely on the table if you ever do injure your spine. Okay, but stress fractures are also common as well. So if you remember, we talked about stress fractures being fractures that occur through repetitive use. Okay? So maybe you're not applying a huge load to your spine, but maybe you're constantly exposing the spine to these repeated injuries or repeated stresses, and that can cause a stress fracture. Okay. All right, and so the unfortunate thing is that spinal fractures or stress fractures are very difficult to heal on their own because there's just so much loading on the spine in general. It's just the spine doesn't have a lot of chance to kind of heal or kind of repair its tissue. Okay. Even when you're laying down, your spine is still kind of under certain risk. Okay, so this is probably the injury we talked about the most kind of before getting to this point, which is a disc herniation, right? And so remember we talked about that in between each of your vertebrae bones is kind of this kind of like cartilaginous kind of fluid filled kind of substance called a disc. Okay, and that's mostly there to kind of prevent any kind of contact injuries between the bones, and so that's there to kind of act as a cushion. But if you kind of squeeze it enough, or if you kind of expose it to stress enough, it can start to kind of leak out of that little area between the bones. Okay, and if that disc kind of juts out and kind of protrudes and kind of impinges on your spine, so it starts to pinch on your spinal cord on the nerves, it can cause severe pain. Okay, and so people often confuse this, and so it's not the disc itself that feels pain. So it's not the actual cartilage, it's not the actual tissue there that you feel pain from. It's the fact that tissue is kind of jutting out and kind of pinching your spinal cord. That's what causes pain. Okay, because remember, your spinal cord is a huge bundle of nerves, like the biggest bundle of nerves that you have in your body. So when you have things that are pinching on it or poking at it or compressing it, it's going to cause a tremendous amount of pain. Okay. All right, and so you can have a disc herniation either from a traumatic injury, so you can either have an acute cause, or it can be from stress as well. So it can be from just repeated stress, just like the other type of injuries. Okay. All right, and so the most common location for disc herniation is at the bottom of the cervical vertebrae, or near the bottom of the lumbar vertebrae. Okay, so places that are most commonly exposed to the highest compressive forces. Okay, and I think what's difficult to diagnose a herniation is that if you want to see that cartilage and that soft tissue, you need to get an MRI or a specialized scan, because it doesn't show up on the X-ray. Okay, and so normally, when you do have a herniation, when it's kind of too late, if you take an X-ray, you can kind of see that the space in between your vertebrae bones is reduced. Okay, and so a doctor can usually see that and say, oh yeah, you have a herniation. But early detection is very difficult because if you take an X-ray of that area, then it doesn't actually, that space doesn't actually decrease until it's kind of too late. Okay? By the time it's too late, you're going to be in a lot of pain, and you can tell the doctor very angrily that yes, I have a herniation and it's very painful. I appreciate it if you confirm what I'm feeling right now. Okay. So most of the times, if you do have a herniation, they are fairly conservative because you typically want to be careful in that area. You don't want to do any kind of surgery or any kind of procedure on the spine just because the risk of damaging the spinal cord is very high. But if you have a very severe case, then that may require you getting surgery. All right. Any questions on any of this so far? Okay. I think it's the last one. So the last one here is whiplash. Okay. So whiplash is probably an injury you've heard of, when you get into a car accident. And so what happens during whiplash is that, if you are, if you're driving a car and you kind of hit something, what could happen is that your neck can kind of almost snap forward. Okay? And so that sudden snapping can cause injuries in the cervical spine, so kind of in the top area of the spine. Okay? And kind of the bad thing about whiplash is that a lot of the symptoms can kind of persist over long periods of time. And so if you've ever been in a car accident, maybe someone kind of hit you from behind, they usually ask you that, if you need to go to the doctor, and more importantly, should the other person's insurance pay for it? And maybe right after the car accident, maybe a few days after the car accident, you may feel fine, but then, the pain usually doesn't come for at least another week after that. And so what I always tell people is that, if you're ever in an accident, if you're ever hit from behind, at least go to the doctor and see, while you still have their insurance on the hook. Because if you come to them maybe a week or 2 weeks after that, then they're not going to want to pay for it. And then treating your whiplash is going to come out of your own pocket, which is bad. Okay. All right. And so that's it. And so that's it for the spine. Okay. So that's I did kind of want to finish this. I did want to finish this just to kind of complete this whole unit. But let's go ahead and move on to human dynamics. Any fun questions on the spine or whiplash or anything before we move on? Because we're gonna shift to a completely different process. Okay. And stop sharing here. All right. Okay. So let's go ahead and shift gears. Okay. And so from here on out, we're going to be talking about human dynamics and spots. And so when I say dynamics, what I really mean is motion. Okay. And so we're going to talk about, how do we quantify motion? How do we usually track it? So in maybe next week, we'll actually talk about motion capture. It's kind of a new kind of exciting area. And then we'll talk more about, how do we take motion? How does that affect the amount of forces that your joints and your muscles have to undergo? But we're going to start actually with a fairly specialized topic. And I do this kind of for a very specific reason, because so the topic that we're going to go over is called Gait Biomechanics. Okay, so that's Gait spelled G-A-I-T. And so your gait, if you've ever heard that term before, refers to your walking or running motion. Okay, and so we're basically going to look at the biomechanics of how people walk, how people run, and how that affects the muscles and the joints. Okay. All right, and so we're gonna start with a discussion of human locomotion, walking and. Okay. So it's a little bit of an unusual presentation. So usually when you're starting essentially we're starting a brand new topic here. Usually you kind of start from kind of the foundations, the principles, and then kind of work your way up to kind of the more specialized topics like the gait. Okay. But the reason I do this is because I think walking and running is something that's very familiar to a lot of people, right? And so a lot of time for most people you're going to walk to places, so that's how you get from point A to point B when you're not stuck in traffic on the 57, right? And that's how you usually get around. And if anything too, when you're outside, when you're on campus or something, and you look outside. You kind of observe people walking and running. So it's something that's just kind of a part of just our very everyday life. And I think, and for that reason, I think it serves as kind of a great way to kind of introduce a lot of kind of these new topics that we're going to go over. Okay, because this whole unit on human dynamics, we're going to draw a little bit on what we've learned before, but just a lot of the terminology, a lot of the concepts are going to be kind of quite new, but they're unique to human motion. And so I think presenting it in a way that's kind of you can kind of tangibly see it, I think is something that's going to be beneficial for all of us. Okay. Okay. All right, and so to that end, we're going to focus on kind of two main things. Okay. And so human motion. Human motion analysis. Human motion analysis relies on two, what I call them, kind of steps to work. Okay. And so you should be familiar with these steps, and so they shouldn't be all that different from your dynamics class that we've taken before. Okay. And so on the one hand, we rely on kinematics. And when I say kinematics, what I mean is quantifying and describing the motion that's observed. And so, of course, with kinematics comes things like position, angle, velocity, angular velocity, acceleration, angular acceleration. Okay, so all of those terms. And so, we're going to spend quite a bit of time talking about how to apply those terms to human motion and kind of what are the conventions that we use for kinematics. Okay, that's when we're going to talk about motion capture. And then the other step is dynamics. And so when I talk about dynamics, what I'm talking about are the forces, the torques, the moments, which in this case are going to be provided by primarily the muscles that cause the motion. And so as we talk about gait biomechanics, as we talk about kind of walking and running, I want you guys to kind of keep these two kind of pillars or these two steps in mind, because there will be certain times when we talk about the kinematics of walking and running, and so we'll talk about things that how does the angle of your knee change as you walk, okay? And then we're going to talk about dynamics as well. So things like what are the ground reaction forces? So as you go through, as you take a step, what kind of forces is the ground kind of exerting on your body, and what kind of muscle or what kind of forces your muscles kind of experience as well. Okay. And so hopefully two concepts that are familiar to you guys. It's just again applying it to kind of a biomedical or biomechanical sense. Okay. And another thing I want to kind of mention here is that walking and running are motions that I think a lot of people consider to be fairly simple. Right. And so it's something that a lot of us do kind of without thinking, right? And so when you need to get from point A to point B, if I were to walk to the door right now, I'd just walk there and probably, the things that are on my mind, am I gonna be on time for my next appointment? Do I need to go to the bathroom? Do I need to speed up? Is my shoelace untied, right? So the last thing that's on your mind is actually, coordinating your muscles to actually take a step, lift your foot off the ground and take another step. And so it's something that's kind of, second nature to most of us, right? But in reality, if you actually analyze, something simple like walking from a biomechanical point of view, it's actually a very, very complex thing. So even walking, right? So we're not even getting to running. Walking requires basically the coordination of dozens of different muscles in your body, all working together, all kind of working at the, and timing things down to almost a millisecond. And so if you've ever kind of watched a baby kind of walk, it's always kind of, well, it's very cute, first of all, but it's also very kind of amusing to kind of see them kind of take very awkward steps or kind of move their legs in kind of awkward ways, right? That's because it's hard. Walking is actually a very difficult, thing to accomplish. Ask anyone that's ever designed a walking robot as well. And so to design a robot that walks naturally like a human does is really, really difficult. I think only now, we're getting to a point where, we can do that. But it's taken millions or billions of dollars in research in order to make that happen. So it is a very complex thing. And so, as we go through these next couple lectures, I'm gonna give you guys a lot of kind of figures and a lot of kind of graphs, right? And it's going to be very complex, and because walking is very complex, and that's why there's a lot of research that goes into. All right. Any questions on this so far? Okay. So let's talk about the gait cycle first. So we'll start with walking, and then we'll probably get to running maybe on Wednesday. Let's talk about the walking gait cycle. All right, and so when we first talked about kind of the kinematics of walking, we described it as a cycle because it's basically kind of a repetitive motion. So you're going to take a step, your foot's going to lift off the ground, you're going to take another step, and then that second step, your body's basically doing the same thing as it did for the first step. Okay, and so what you're going to see is if you kind of watch someone kind of walk in place, they're kind of doing the same motion over and over again. Okay, but with that said, we can kind of break up that motion into different stages and kind of analyze biomechanically what's happening in each of those stages. Okay. Okay. And so first let's define kind of what defines one full cycle. So one full gait cycle. One full gait cycle is defined by two consecutive step downs, basically. So when the same foot kind of steps down twice, and so on that second touchdown, that's one full cycle. So I'm going to do my best to draw this. This is what I was kind of dreading today. And so let's see. Okay, so I have 1, 2, 3, 4, 5, 6. 6 stick figures to draw. Right, and so in all these figures, we're gonna follow primarily the right leg, okay? And so this person is gonna be walking from left to right, okay? And in terms of the gait cycle, we're gonna define it relative to the right leg. So the left leg will be there. It's just that, we're just not gonna focus. Okay. Okay. And so the first event that we have here is the initial foot contact, okay? And so the leg that we're focusing on, I'm going to draw in solid, and then the other leg is going to be dark. Okay. And so first event is just straight up foot contact. And so if you notice that for most people when they take a step, they lead with their heel, right? And so when they step down with their heel first, and then let the rest of the foot fall. We make sure that this person has a consistently sized head. It didn't change. Okay, so the next stage in the walking cycle is what we call foot flat. Okay, and so the foot that we're following is going to be planted on the ground with the entire foot. Okay. While the other leg is doing something like that. Okay. Next stage, and so the next stage we're preparing to take a step, and so the first thing that comes off the ground for most people is going to be the heel, and so the next stage in the walking gait cycle is called heel off. So it looks something like this, or the other leg, maybe like that. So this is heel off. Then after the heel comes off, then the toe usually comes off. And so at this stage, we've entered what's called the swing phase of the walking gait cycle. And so when we say that your foot is in swing, what we're saying is that the foot is no longer on the ground. Okay. Then while your foot is swinging, then we have another stage where your knee reaches maximum flexion. Okay. And so in order to make sure that as your leg kind of swings forward, your foot doesn't drag on the ground, you kind of bend your leg at your knee as much as possible. So we call this the knee flexion stage. Something like this. And then once your leg kind of swings forward, your knee straightens, and then you kind of enter the gait cycle again. So you enter heel down, foot contact stage. Okay. So the last stage that I'm going to draw here is the exact same as the first stage. Okay. So those are all the different stages of the walking gait cycle. Okay. So you have foot contact, foot flat, heel off, toe off. Once your toe is off, then you're in the swing phase. Then when your leg is swinging forward, your knee is flexed. And then once your knee straightens out, then you contact the ground again with your heel, and you start it all over again. Okay. Okay. And so let's go ahead and define the different phases. So I've already talked about the swing phase here. Okay. And so the swing phase is basically here. And so the swing phase is when your foot is off the ground, so that's you know, a swing forward, hence the name swing phase. Okay. And so for a typical person, and so it varies person to person, depending on the length of their legs, you know, for instance. Swing phase is about 40% of the gait cycle, okay? And then for all the other phase, for the other parts where your foot is on the ground, we call this the stance phase. Forgot how to spell stance phase. And you spend about 60% of your of the gait cycle in the stance phase. And so you spend more time, or your foot spends more time on the ground than it is in the air. Okay. And in fact, you know, there's a period of time in your walking gait cycle, and you know, and I know right after this class, everyone's going to go out and kind of watch people walk, see if it's true. There's a part of the walking gait cycle where both of your feet are on the ground. Okay. And so we call that phase the double support phase. So that is roughly about here, between this phase and double support. Okay. And we also have a double support phase kind of over here as well. And so there are basically two times during the walking gait cycle where both your feet are on the ground. So we call that double support. And each of those are about 10%. Okay. All right, so the double support phase is very important. And that's kind of what distinguishes walking from running. Okay. And so we'll talk about this kind of when we get to running on Wednesday. But what kind of distinguishes walking from running is that, you know, when you're walking, you have a double support phase where both your feet are on the ground. In running, we have a phase called the flight phase, where neither of your feet are on the ground. So you're literally kind of jumping from step to step. And during that time when both your feet are in the air, you know, although briefly, we call that the flight phase. Okay, and so that's kind of the main difference between walking and walking. All right. Any questions on this so far? Okay. All right. So actually, you know, I've thrown a lot of terms here. So let me give you the exact definitions. Okay. So first we have the stance phase. And so these first two terms here are referring to a single leg or a single foot. Okay. And so the stance phase for a particular foot is when that foot is in contact with the ground. The other term we went over was the swing phase. Same mistake as before, H. Stance phase and swing phase. So the swing phase is when the foot is off the ground. Then the last term was double support. So double support is a phase that kind of for, you know, the person overall. So it doesn't refer to just one foot, because the double support phase is when both your feet are on the ground during the walking gait. And the reason you have this is that for a typical walking gait cycle, the stance phase is longer than the swing phase. Okay, so your foot spends more time on the ground than it does in the air when you're just walking. Okay. Okay. All right. So those terms, we'll continue to kind of use those terms throughout this chapter. Okay. All right, so let me give you some more terms. And so these terms are more for kind of the kinematics of walking. Okay. Just a lot of definitions today, but we just need to kind of get them all out of the way. All right, most of these are fairly simple. So first is step length. Okay. And so the step length, just like the name implies, it defines how long your step is. Okay. And so the exact definition is the distance along the line of progression and so the line of progression refers to kind of the direction that you're walking in. Okay. And so if you were to draw a line, kind of, if I were to kind of walk to that door and back, the line of progression would kind of go straight from here to that door. Okay. And so the step length is the distance along the line of progression between the same point on two consecutive footprints. Which is a fancy way of saying, how long are your steps? Okay. All right, so we also have the stride length. And so the stride length is the distance traveled in two consecutive footprints or in one full gait cycle. Right, so two step lengths ideally should be the same as a one stride length. Okay, so you take two steps, that's one gait cycle, that's your stride length. Okay. Next, we have the step frequency or the cadence, and so this is basically how quickly you're walking, how quickly you're taking steps. Okay. And so its exact definition is the rate at which foot contact events occur. Next, we have the stride frequency, and so stride frequency. So kind of the relationship between step length and stride length, step frequency and stride frequency is the same. So the stride frequency is the rate at which strides occur. All right, and finally, the most probably the most important or kind of the most you know most recognizable stat in walking is your walking speed. So that basically the horizontal velocity that you have going forward when you're walking. And so the way you find the walking speed is very simple. So and so you basically just take the product of either the step length and the step frequency, or the stride length and the stride frequency. Okay. Very simple. So it's just a distance multiplied by frequency. Okay. And so of course, I know what you're probably all wondering. So what are some typical numbers for all of these? Okay. You can go home and measure the length of your leg with the stick and see how you measure up to the average person. Okay. And so the typical step length. And so the typical step length for a normal person is between 0.6 and 0.7 meters. Okay. And don't cheat. Don't go home and take a gigantic step like, wow, I take big steps. Like, be honest, okay? And so this typical step frequency is just about around 2 steps per second. And so, for most people, the speed that they normally walk, they take kind of 1 full stride per second, which is quite convenient for calculations. And so if you multiply those two together, then what we have is a typical walking speed. Typical walking speed of about 1.2 to 1.4 meters per second. All right, so a lot of terms, but a lot of these are kind of duplicates or very similar to each other, and hopefully not too difficult to understand. All right. Any questions? Any questions on this so far? Okay. All right. So last thing I want to talk about today is this idea of ground reaction forces, which is something that's kind of unique to walking. But again, this will kind of feed into kind of our discussion later in the class about kind of external forces and how that affects our muscle movements. Okay. Okay. And so like the name implies, ground reaction forces are, reaction forces that come from the ground. And so as you kind of take steps, the ground is going to exert an equal and opposite force, on you, okay, just to kind of keep things in equilibrium. But the ground reaction forces play a very important role because, if you think about it, the muscles or the forces that your muscles exert, those are all kind of purely internal forces. So what I mean by that is that if you kind of consider your body as a whole, it doesn't really matter what your muscles do, it's always going to be an internal force. And the thing about internal forces is that it's literally impossible to cause external movement or movement of the entire body purely from just internal forces. And so despite what some people might tell you, it is literally impossible to pull yourself up by your bootstraps. You need to pull your bootstraps up, attach it to something, and then pull yourself up from that. And it's the external force that something puts on your bootstrap that can kind of pull yourself. Okay. So walking is the same way. And so your leg muscles by themselves cannot move your body. And so what actually happens is that your leg muscles actually drive forces into the ground, and the ground's normal forces that come back, that's actually what moves your body forward. Okay. So that's a very important distinction, right? And so, even though it seems like yes, when you drive a force into the ground, what comes back is an equal and opposite force, right? So that's Newton's third law. But the fact that the normal force from the ground is technically an external force, right? And so you didn't explicitly produce that force, you explicitly only produced the muscle force, right? The fact that that ground reaction force is external to your body, that's what can move your body forward, okay? All right, comment. So that's why it's more difficult to walk on a sandy beach. You don't get all that force back. Exactly right. So that's exactly the case. Yeah, and walking on difficult terrain is also kind of a very interesting subject for robotics actually as well. So, yeah, very, very interesting. Okay. And so if you were to kind of move anywhere, you need some kind of external object. Okay? And then when you actually move your body, the way that you can think about it is that you're kind of pushing off on some kind of external object, and then that external object actually is what moves you, as opposed to kind of you self kind of moving yourself, which is kind of a difference kind of. Okay, so let's just kind of let's stop here for now, because the next thing that comes is kind of diagrams and stuff, and that's not something you want to do over at 5:14. Okay, and so we'll pick up with this on Thursday or Wednesday. Sorry. Any questions on this before we wrap it up today? Okay, all right, and so thanks guys for coming today. Hope you guys enjoy the rest of your day. I'm going to try to get the midterms graded by Wednesday. It's just so you know what we have, but if not, by the end of, so it'll be posted on Canvas kind of as soon as I'm done with it. All right, so thank you guys for coming. I hope you guys enjoy the rest of your day. I will proceed on. Yes. Yes, so after I'm done grading all the midterms, I will post the solution. Yeah, so I think it's complicated about that is that. So I won't be able to release them until they take.